Hello everyone, welcome back to MP Coding, and this is the Linux Device Driver Development Series. Today, we are starting Section 4 of the series. In today's video, let's look at the Linux I2C Subsystem basics. I2C is a synchronous serial communication protocol that uses a simple two-wire interface to connect low-speed peripheral devices. It is commonly used to communicate with devices such as sensors, EEPROMs, real-time clocks, ADCs, DACs, and power management ICs. The protocol was originally developed by Philips, and today it is supported by almost all major IC manufacturers. In Linux-based embedded systems, I2C plays a very important role because many external peripherals are connected using this bus. Linux provides a generic I2C framework that abstracts the hardware details. This means that, as driver developers, we do not directly control the I2C hardware. Instead, we interact with the Linux I2C subsystem, which handles communication in a standardized and hardware-independent way. If we look at what I2C is, the I2C bus is a two-wire bus consisting of SDA and SCL lines. SDA is the data line, and SCL is the clock line. Both lines are open drain and require pull-up resistors. I2C supports multi-master and multi-slave configurations. Each device connected to the I2C bus has a unique address, which can be either 7-bit or 10-bit. During an I2C transaction, the master device generates the clock on the SCL line and initiates either a read or write operation. After every 8 bits of data, the receiver sends an acknowledgement bit to indicate whether the transfer was successful. I will not go into a detailed explanation of the I2C protocol here. You can search online for more information if you want. Now let's look at how Linux models this I2C bus internally. The Linux I2C subsystem is the interface through which the kernel communicates with devices connected to the I2C bus. In Linux, the kernel always acts as the I2C master. The I2C subsystem is logically divided into two main parts, buses and devices. On the bus side, we have adapters and algorithms. On the device side, we have clients and drivers. In the bus side, the adapter represents the I2C controller hardware. The algorithm defines how transfers are performed. In the device side, the client represents a physical I2C slave device. The driver contains device-specific logic. Now let's look at the three main components. I2C core. The I2C core provides a common infrastructure for all I2C drivers. It handles the registration and removal of I2C adapters, the registration and removal of I2C client drivers, device driver matching, and common I2C APIs such as I2C_transfer. Next, I2C bus driver, the adapter and algorithm. The I2C bus driver represents the I2C controller hardware present on the system on chip. It is responsible for generating clock signals, handling start and stop conditions, and physically transferring data over the SDA and SCL lines. This part of the subsystem is described using two main structures, struct I2C_adapter and struct I2C_algorithm. Typically, the adapter driver is implemented as a platform driver. Next one is I2C client driver. The I2C client driver represents a specific slave device connected to the I2C bus, such as a sensor or an EEPROM. An I2C client driver consists of struct I2C_driver for driver logic, and the struct I2C_client for device instance. When the I2C core finds a match between a client and a driver, it calls the driver's probe function. All I2C related code in the Linux kernel is located under the drivers /I2C directory. If I show you the Raspberry Pi Linux kernel source code on GitHub and go into the drivers /I2C folder, we can see all the I2C related files. I2C core.h file for core I2C framework. I2C dev.c file 4, generic user space I2C. I2C/buses APIs for legacy or specific device drivers. I2C/algos APIs for I2C transfer algorithms. There are two main ways to use I2C in Linux. The first method is using I2C dev. The second method is writing a dedicated I2C client driver. In the first method is to use the generic I2C dev driver, exposes I2C adapters as device files like /dev/I2C1, allowing user space applications to directly communicate with I2C devices. Used for testing and prototyping, common tools like I2C tools. The second method is to write a dedicated kernel-space I2C client driver for a specific device. Recommended for production systems, better performance and integration, fully managed by the kernel. In this video series, we will focus on writing proper I2C client drivers. Now that we understand the Linux I2C subsystem conceptually, let's look at how I2C appears in a running Linux system. First, let's enable the I2C interface. Type sudo rasp-config and press enter. From the menu, go to Interface Options. Then select I2C and enable the I2C interface. Now let's look at the user space device directory. Here, you can see multiple I2C adapters exposed to user space. For example, I2C1 means I2C adapter number 1. These device nodes are created by the I2C dev driver. Applications and tools such as I2C tools use these device files to communicate with I2C devices directly from user space. An easy way to check whether the I2C interface is working is by using I2C tools. You can install it using sudo apt-get install I2C tools. I have already installed it. Now let me show you some useful commands. If we type I2C detect-l, we can see all I2C adapters registered with the kernel. This command also tells us which I2C controller driver created each adapter. Next, if we type I2C detect-y1, this scans I2C bus number 1 and shows all slave devices that respond to I2C addresses. Each detected address corresponds to a physical device connected to the bus. Here, the hexadecimal value 77 indicates that I have connected a BMP180 pressure sensor to the I2C1 bus, and its ID value is 77. In the next video, I will show a complete example using the BMP180 sensor. So remember these simple commands from the I2C Tools application, because we will use them again. Another important thing in real embedded Linux systems is understanding the device tree. If you are familiar with the Zephyr project, you may already know about device tree concepts. In this series, I will create a complete tutorial on the device tree. Most modern embedded Linux systems use device tree to describe hardware. For now, I just want to show you how I2C configuration is registered in the device tree. This command converts the live device tree from the running kernel into a readable DTS format and creates a file called tmp_dt.dts. If we look inside this file, we can see that it is quite large. It contains hardware-related information such as memory locations, naming tags, clock configuration, and other properties. I will explain these details in a separate video. Now let's look at how I2C controllers are described in the device tree on this system. At first glance, you may notice many I2C nodes in the device tree. This does not mean that all of them are active. Each I2C node represents a potential I2C controller hardware block inside the system on chip. Whether it is actually used or not depends on the status property. The status equals OK property tells the kernel that this I2C controller is enabled. Only I2C controllers marked as OK will be probed by the kernel and appear in the /dev directory as I2C devices. All other controllers marked as disabled are ignored. Now let's see how this maps to /dev/I2C1. When the kernel boots, it scans the device tree. For each I2C controller node with status equals OK, the corresponding I2C adapter driver is loaded, and an I2C adapter is registered. That adapter then appears as a device file, such as /dev/I2C1. The exact bus number is assigned dynamically by the kernel. The compatible property is used for driver matching. It tells the kernel which driver can handle a particular hardware block. In this case, the Broadcom I2C controller driver supports both BCM2711 and BCM2835 variants. The reg property specifies the memory mapped register address and the size of the I2C controller. This information is used by the adapter driver to access the hardware registers. The clock frequency property defines the I2C bus speed in Hertz. This hexadecimal value corresponds to 100 kHz, which is the standard I2C bus speed. Some of the other I2C controllers shown here are dedicated to HDMI. They are typically used internally for communication between the system-on-chip and HDMI components, such as reading EDID information. Even though these are I2C buses, we usually do not attach external devices to them. I will be creating a dedicated set of videos in the future where we build complete device tree examples step by step, covering GPIOs, SPI, I2C, and other peripherals in detail. So for now, we'll just look at this from a high-level point of view. Now let's explore I2C via sysfs from the kernel point of view. If we look at the directory /sys/class/I2C this directory shows all I2C adapters registered with the kernel. Each entry here maps directly to /dev/I2C device file. If we look inside I2C1, this directory links to the actual I2C adapter device in the Linux kernel device model. Now, if we look inside the device directory, here we can see adapter-specific files, including the ability to dynamically create or remove I2C client devices. Now let's see how we can create a new I2C device dynamically. This command dynamically creates an I2C client device on bus I2C1 with address 50. To run this command, first switch to the superuser. Type sudo su and hit enter, and then run the command. The string EEPROM must match an entry in the I2C_device_ID table of a registered I2C client driver. Once this command is executed, first the kernel creates a new I2C_client. Then I2C core searches for a matching driver. Finally, if a match is found, the driver's probe function is called. Now, if we look at the I2C devices, here we can see a new device. This means bus number 1 and address 50. This is how we can create a new I2C device using the terminal. In a future video, I will discuss how the same thing can be done automatically when a kernel module is loaded. To clean up the created device, use this command. This removes the dynamically created I2C client and calls the driver's remove function. If we look at in simply how user space and kernel space connect. User space interacts with I2C through device directory I2Cs using the I2C dev driver. And the kernel drivers interact with I2C through the I2C core using APIs such as I2C_add_driver and I2C_transfer. Both views represent the same underlying I2C subsystem. That's it for today's video. Today, we looked at the basics of the Linux I2C interface. In the next video, we will implement a complete I2C example using the BMP180 sensor. So stay tuned. If you found this video helpful, please like the video, subscribe to the channel, and hit the bell icon to get notified about upcoming videos. Thanks for watching, and I'll see you in the next one.